welcome everybody. Welcome back. This is the first seminar of the new term. Today we have Jure Vogrinc talking about counterexample for optimal scaling of Metropolis Hastings chains with rough target densities. Please, Jure.
Okay, thank you, Massi. So thank you everyone for being here on this bank holiday weekend. So let's get on with it. So some of you have seen this talk before, and or like parts of this talk, but the end is I've added some new stuff towards the end, so hopefully it's going to be interesting for you as well. So here's how I imagine it will go. So I will review some of the classical results about optimal scaling of MCMC algorithms, just to basically, because not everyone has been doing this, obviously. And then we'll look at the rough counterexamples that me and Willfit came up with. And we'll also talk about the mathematical background behind it. And most of this is based on this paper that got published in the Annals of Applied Probability recently. That is joint work with Willfit. And at the end, I will also talk about a different application of the same mathematical background, which I'm going to call locally balanced first order Metropolis Hastings, which is joint work with Sam Livingstone and Giacomo Zanella. So that one is test work, not published yet. So we will be the test audience, and any feedback is welcome. So just to basically fix the notation, I'm sure that all of you know what Metropolis Hastings is, but basically we have a target in Rn, like a probability density that we wish to simulate from. And we do that by Metropolis Hastings algorithm, the simplest MCMC method, or at least the first. So you start somewhere, and then you iterate the following scheme, right? You generate a proposal that depends on your current location from some density. You can think about adding a normal increment to wherever you are, and then you evaluate this number called the acceptance probability, which is the minimum of 1 and this ratio here. And then finally, you toss a coin with heads probability alpha. And in case of heads, you accept the proposal and move there. And in case of tails, you stay where you were. And what this does is it generates a correlated sample that is distributed increasingly according to pi. And of course, to make this a useful thing, we want this correlation to be as small as possible, and we want these things to be distributed as pi as fast as possible. Right? This is what we would like. And somehow you are given pi. I mean, this is how it generally is. Like you are given pi, but you can choose q for yourself, let's say. So a very natural question here is how do you choose q? And this is something that we would like to answer, but even this is in itself like a too difficult question. So we basically narrow it down to like particular forms of Q. So we're going to look at simpler particular forms of Q. The simplest is called random walk metropolis, where basically the proposal density of going from X to Y depends only on the distance between X and Y. And in this case, the acceptance probability simplifies to this form, like this ratio is simpler, the ratio of Q vanished, basically. And this is an example of this is when you add a normal increment to your current location to propose. And then another example we're also going to look at is called Metropolis adjusted Langevin algorithm, or MALA, where you also add a normal increment, but you don't center it to where you are, but you move the center slightly in the direction of the gradient of your target. So we will come back to these two algorithms later, but already here it's like a natural question to basically ask. Let's say that I have this, right? I'm doing a normal increment around where I am. The question, a perfectly valid question is, how do I choose the variance of this normal increment, right? So how to choose the variance in random walk Metropolis with normal proposal, and if you run some tests, you see very quickly that that if you choose the variance too big, you're going to propose far out into the tails, and lots of your proposals are going to be rejected. And this is going to end in you standing still for large periods of time, and you will get a graph that looks like this, right? So how good is this graph? You need to imagine that you project it on the left axis, and you should get something that looks like a target distribution. And of course, here you don't, right? So this doesn't work well at all. And on the other hand, if you choose sigma too small, I mean, it's arguably better than the other thing, but it looks like too much like a diffusion, which means that it sort of spends way too much energy, way too much effort is spent on oscillating on the spot rather than exploring. You can see here that for going from -1 to I don't know 1.5, it needs like thousands of steps, right? And it's not hard to see basically that something in between is doing a better job. But then the question is, can you say something smarter than this? And here's where I'm going to review some of the classical results. You can do something better, smarter than this. So let's say that now you have a density on real numbers, so just a one-dimensional density. And now we are going to look at a sequence of random walk metropolis chains. Okay, so the first chain lives in R. The second chain lives in R squared. The third chain lives in R3, and so on. And the nth chain is going to have a target that is just n copies of the target multiplied together with itself, and it's going to have a normal proposal centered at the current location with some variance. With actually variance that scales as 1 over n, with the n being the dimension. And if you think about it, because of the normal structure, this also has a product structure. The proposal density also has a product structure. Then Roberts, Gelman, and Gilkes have shown the following thing in 97. They've shown that if you take the nth chain, the one that lives in n dimensions, and you make a continuous time process out of it by jumping at the constant rate, and accelerating it by a factor of n, and then finally looking at only the first coordinate of the process. Then this collection of processes converges weakly to a Langevin diffusion. Okay, this is this diffusion here. It's a one-dimensional diffusion, and it has pi as a stationary measure, and it has this parameter HL that describes the speed at which this diffusion moves. And the idea is that the faster that this diffusion moves, the better it explores the space, the faster it mixes in some sense. And hopefully the same is true for these chains converging to it. Right? That basically if you make this speed parameter HL larger, the thing will work better. And there is like an explicit formula for this HL, which I don't have here, and it's not particularly important. The important point is that you can optimize this HL in terms of L, and you get what you get is that this HL takes the highest value when you accept on average this fraction of proposals. So 23.4% of proposals. Now, what I want to say here is that this rate, what is important here is that this rate, variance proposal rate, 1 over n, is the only rate which gives you a non-trivial limit here. Right? Any other rate will basically make this explode or make this converge to 0, and any other rate will make the acceptance rate go to 1 or to 0. Okay, so this is a famous result by Garrett, Gelman, and Gilkes that leads to this famous heuristics that you should tune your random walk metropolis to basically accept roughly 1/4 of steps. And this is of course proven in like this toy example that I'm telling you here about, but this is not somehow so bad for a few reasons, because somehow it's a good model for the part of the space that you don't know anything about. In some sense, it's like saying that the coordinates, the marginals of your target are independent, is a bit like saying that they're exchangeable, and then in some sense it's not. So somehow these things actually is quite a robust result, despite being only proven in like toy situations such as this one. And the second thing is why this is a very popular thing is because it's easily measurable by a practitioner. It's very easy to tune, right? It's not something complicated to tune. Okay, so but this result, right, is not. There are some prerequisites for this. There are some assumptions for this result. The pi needs to be positive everywhere, and it needs to satisfy certain moment conditions, and it has to satisfy these assumptions. So pi has to have at least two derivatives. And this is where we get to my and Wilfried's work. So the question is, do we need this assumption C2? Right? In the original paper, C2 was used. It's no, is this an artifact of the proof or is this something natural? And so Zanella, Bedard, and Wilfried Kendall, they showed that actually one derivative and a bit is enough, and you can do the same thing. And these people have shown in the same year that something that I will casually interpret here as pi can be non-smooth on a measure zero set. So things like Laplacian target, things that have discrete amount, that have like a finite amount of spikes, but are otherwise smooth, it works for them as well. So this result is valid for them as well. And then the natural question is if we can go beyond C1, and this is what we proved with Willfit. We can't go beyond C1. So any holder continuity less than 1 is not good enough. Now I think this is like interesting result in itself because it says something fundamental about one of the most basic MCMC methods that is also used as a subroutine in different more complicated MCMC algorithms. So I would say this says something fundamental about the method. And secondly, it's a bit surprising because to actually make the Metropolis Hastings target and be ergodic, to make it target pi and be ergodic, you actually need much less. You don't even need continuity. But you need at least one derivative for it to behave as you would expect. Now, of course, you could say that this doesn't really. If you look at these results here, right, this tells you that anything you can potentially think of will satisfy these things. Like no one wants to simulate from things that if spikes are fine, that no one cares about things that are like, I don't know, everywhere rough and stuff like that. First of all, you can interpret a rough target as a noisy observation of a smooth target. That's my first remark. And the second remark is that I'm going to show an example in 2 slides that will make you rethink this, that this is irrelevant. Okay, but first let's see the counterexamples that we cooked up with Wilfried. So basically, they are given as random examples. So basically, they're given in terms of fractional Brownian motion. So fractional Brownian motion is a Gaussian process with this covariance structure, and the important property is that its paths are almost surely alpha holder for any alpha less than h. And if you're uncomfortable with this, just imagine Brownian motion, which happens when h equals 1/2. And the random target is given like this. So basically, this is the target. It's like a Gaussian, but it's perturbed at the level of a potential. It's perturbed by a path of a 2-sided fractional Brownian motion. Okay, so it's like a random rough target, and this is like just one simulated example of such a target. And the theorem that we showed is that for almost every fractional Brownian motion path, the optimal scaling rate for proposal variance for this target is n to the -1 over h. So in classical results, this should be n to -1. But this is worse. This is worse than the other thing. And this result, we've proven it, the optimality in terms of something called expected square jump distance, which doesn't really matter what that means. But it's basically a measure of efficiency. And this is enough to, it doesn't say that the diffusion limit exists with this scaling, but it does say that the classical situation cannot happen. Like if the classical situation would, if the outcomes of the classical theorems would hold, then basically you would have to have here n to the -1. And so this as well, this you can then set the proposal variance as with this rate, and you can put the constant L squared here, and you can optimize over L. For any given h, you can optimize over L, and you can get the optimal acceptance rate for various h's in these cases, right? And the curve looks a bit like this. And for example, for h equals 1/2, you basically, it's optimal to accept 7% of proposals. And for h equals 1/4, it's optimal to accept less than 1% of proposals. Which basically somehow says, in my opinion, that random walk Metropolis doesn't really work on non-smooth things. Like, I mean, it's really bad. If you need to invest like hundreds and thousands of steps for it to basically move once, and that's optimal. Okay, and here is an interesting example. So we looked at a different perturbation. So this is also, it's a different target. Again, a perturbation of a Gaussian, but not perturbed by Brownian, fractional Brownian motion, but by something smooth, something nice. And we took these constants, and we took this target 100 times multiplied with itself. So a 100-dimensional target, and each marginal looks like this. And we tuned it to basically to accept 23% of proposals, and it gave this expected square jump distance. Basically, this is a measure of efficiency. The bigger, the better. So it gave this, and this is how like a trajectory looked like. And then we tuned it to basically 7.7%, and it gave a 5 times better expected square jump distance, right? So even in 100 dimensions, and this is a thing that is completely, theoretically, in the limit, is completely in the regime of the classical setting from Garrett, Roberts, Gelman, and Gilkes. But somehow, even in 100 dimensions, this tuning actually outperforms the theoretical best tuning quite a lot. And this is even though this exhibits this sort of weird behavior with basically is just staying still for hundreds of steps. So it exhibits this weird sticky behavior, but still outperforms the other one. And we can do the same thing for Mala. So now we have, again, a sequence of Mala chains. The first one is in 1 dimension, the second one is in 2 dimensions, the third one in 3 dimensions, and so on. Again, the target is n copies of pi multiplied with itself, and the proposal is a Mala proposal. So basically, it's a normal increment centered somewhat. You move the center somewhat in the direction of the gradient. And these two constants here need to be the same. It's important that it's like this. And this also has a product structure because the proposals are essentially normal. This also has a product structure if you think about it. And this time it turns out that we need to scale in this way, right? We need to scale the variance to be of order n to -1/3. And then Roberts and Rosenthal have shown that, again, if you take this thing, you make the nth chain living in n dimensions, and you make a continuous time process out of it, and you accelerate it by this factor n to 1/3, and you look at the first coordinate, then these things converge weakly to Langevin diffusion. It's the same diffusion apart from this speed measure has a different formula, but again, you can optimize this formula. And you get that it's the best when you have you accept 57% of proposals. And again, this is the only rate that gives you a non-trivial limit here. And here the assumptions that they used is that the target has 8 derivatives. And the question again is legitimately, do we need 8 derivatives? And no, actually 3 and a bit is enough. And the question is, can we go beyond 3? No, we can't. We have counterexamples. And again, what's surprising here in some sense is that to run Mala, you only need 1 derivative, and there's even tricks how to run it without, but by somehow having a derivative that is like a difference actually. But so to run it, we need 1 derivative, but for it to basically work as you expect, you actually need 3 derivatives. This is something that would be hard to guess, I think. Maybe the one with Metropolis you can somehow argue, but this one is somehow harder to argue. It really comes down with the Taylor series kind of analysis of the correct thing. And so basically we've shown that having 2 derivatives and the second derivative being any sort of holder, any level of holder, but not having another derivative is not good enough. And the construction again is given in terms of a 2-sided fractional Brownian motion. And the random target now looks like this. So the formula is uglier, but again, it's actually a perturbation of Gaussian. So you take a Gaussian, you perturb it by something. And this is actually chosen in such a way that if you actually differentiate the proposal twice, no, the potential, if you differentiate the potential twice, you see that it's basically a potential that is perturbed. I mean, that is again a Gaussian that is perturbed at the level of the second derivative of the potential. And there's this function here, phi c, that is basically, we call it localization function. It's just there to ensure that things don't explode and that we're in fact dealing with target. But actually, this is somewhat arbitrary almost. And I mean, of course, plenty of these other sorts of things could be constructed giving the same sort of things. At least this is what we think. We haven't actually constructed other ones, but we think that it's not. There's nothing particular about these specific examples. And the theorem here is that for almost every fractional Brownian motion path, again, the optimal scaling rate of the proposal variance for this target that I've just shown is actually n to the -1 over 2 plus h, right? In a classical situation, it should be n to -1 over 3, and this is actually worse. Yeah, this is worse, and again, we can set the variance to be L squared divided by this correct rate, and we can again optimize over L, and we can basically, for any choice of H, we can find the optimal L, the optimal acceptance rate. And we see that for smoothness classes of targets between 2 and 3, we basically get the optimal acceptance rate goes from 45% to 54%. I don't have like a really dramatic example here. We can detect that this actually makes a difference in things that but the difference is sort of marginal. Sort of the Mala still seems to work well for these sort of cases that we tried, like the ones where you're perturbed by like a sinoid or something. Okay, so these are the counterexamples, and now I want to talk a bit about the mathematical background that we used to deliver this. We had to kind of create like a more detailed framework for addressing these optimal scaling questions, because yeah, to basically be able to give these more detailed results. And the crucial concept was what we called log Metropolis Hastings ratio random variables. They are given for a target and a proposal, and they are defined like this. So basically, you take the ratio, the same ratio that appears in the acceptance rate, and you just take a log. And this is a random variable because you take that x is distributed like this and y is distributed like that. And what this effectively does is this measures the failure of Q to be pi reversible. So what I mean by this is that if Q is pi reversible, then the top and the bottom is the same, and this is 1, and basically this is 0, right? So in some sense, if you already have a Markov kernel which is reversible in the first place, then basically these row variables are 0. And then the further link with the information theory via this link the expectation of minus rho is equals the KL divergence between the top measure here and the bottom measure here. So these are somehow the connections, but the proofs rely heavily on particular properties of these random variables. Namely, like if we have a sequence of these random variables, log Metropolis Hastings random variables, right? The nth one, the row n is for target pi n and proposal qn. And then if there exists a positive sequence converging to 0, such that basically the second moments of this row converge, and simultaneously this expression converges faster to 0 for some an going to 0. So this is like a uniform integrability condition, but it's actually weaker than uniform integrability, but it's kind of similar in flavor, and it's something that is tedious but somehow quite straightforward to check in particular examples. And if basically we have a situation like that, then we can say that the expectation of rho and the 1/2 of the second moment of rho, this thing together, basically this sum, decays faster than the second moment, right? So this tells you something kind of very particular about these random variables, and it's then useful in proving the following CLT type result. Because in toy setting, by toy setting I mean if you have a target that is a product of n copies of itself, and also a proposal that is a product of n copies of itself, then you can denote with rho n the log Metropolis Hastings variable for pi n qn, right? Because qn still depends on n, like the variance size of each coordinate, for example. And you denote the rho n bar as the log Metropolis Hastings ratio for the full target and the full proposal, right? Then basically this rho bar n is basically a sum of rho n's which are independent from each other, and these things converge weakly. That's why I'm calling this a CLT. They converge weakly to a normal distribution of this particular form. To get this, we must have that n times e to the rho n squared goes to a constant, and then this constant appears here in this normal random variable. So basically, what this essentially means is that you need to find such a proposal variance that the second norm of you need to find such a proposal variance that the second moment of rho n will decay as 1 over n, and in that case you will get like a normal limit here, and for any other kind of scaling you will get a different for any other scaling this will either go to 0 or blow up again. So in some sense, additionally, right, so basically if we can link the proposal variance of a single coordinate with the decay rate of these second moments of rho n, right? So if we have 2 to the beta for some beta, then we can prove automatically that rho n, that if the variance is scaled as n to minus 1 over beta, this is the optimal decay rate in terms of expected square jump distance. So any other decay rate that is significantly faster or significantly slower than this rate will give you a worse result. Will give you a worse asymptotic expected square jump distance when you go to infinity. And this simply means basically that the curves that I was showing you before, you could basically make this beta as large as you want, and you can still then again optimize over L, and you can get an optimal acceptance rate depending on the decay rate of these rho variables, right? Before I showed you for random walk Metropolis, I showed you this piece of this curve between 0 and 1, and for Mala I showed you this piece of the curve between 2 and 3, right? But this is the curve from 0 to 20 if you want. This is numerical. I mean, it has like it comes out of like a equation that doesn't have the solution is not expressible in these simple functions, but it's basically very numerically stable to compute. And finally, okay, so this is all I wanted to say about the mathematical background. So we used intrinsic properties of these row random variables to deliver these results. And now I'm going to finish by showing you a different line of work where we use the same framework for a different purpose. And what I forgot to say is that this central limit theorem here is really the highlight in some sense, because this is what enables more detailed analysis. Because classic results from Gareth and from Jeff, they also include the CLT, but that CLT is a bit different. It's like condition. This is CLT in both target and proposal random variables, while there it was like for any draw of the target you have a CLT. So it was much more complicated, and you needed to control higher moments of Taylor series for proposal and so on. So this actually simplifies a lot the analysis, this particular CLT. And so now I want to give a completely different application of this same framework. So this is joint work with Sam Livingstone and Giacomo Zanella, so we call it locally balanced proposals. I mean, we call it locally balanced first order Metropolis Hastings. So let's say you have something I'm going to call a balancing function. So it maps positive reals to positive reals, and it's a function that satisfies this functional equation here. Okay. And it will turn out that we will want it. It makes sense to say that it's increasing, and we will just for simplicity say that it has 3 derivatives. And we will also enforce that g of 1 is 1. This is just somehow there is like a choice. There's like a free parameter that we fixed by doing so. And if you choose this g1 to be 1, then this has to be true. You can just differentiate the functional equation, and you can conclude that the first derivative of g at 1 needs to be 1/2. And so what are the examples of such functions? The square root is the simplest. This is the second simplest example, but there's really many examples. Actually, for any even function from reals to positive reals, for any such even function, you can get such a g. There's like a bijection between these sort of functions and even functions. So there's like really a lot of them. But the only other example I want to basically mention is this one, which is basically like a derivative. When you put this is a balancing function for any a. So if you put 0 in, you get the square root. But we want to put other stuff as well. So you have a function with these properties, and you have a symmetric probability density k, for which we want to have finite 6th moment of this probability density. And we want the second moment to be 1. This is, again, the second moment being 1 is like choosing a free parameter in some sense. And we're looking at this locally balanced proposal. So what do? You basically simulate, you basically see, being at x, you simulate from k, from this k density around u, but a rescaled version of it, right? You rescale it and simulate from there, and then you kind of bias the outcome with this factor. And the z is just a normalizing constant, making this a Markov kernel, okay? So this is some weird proposal. So this is a theoretical proposal, and it is, if you think about it, it's pi zn reversible. So yeah, this thing is a stationary measure, and you would think that if you send sigma n to 0, like this thing, so that basically essentially this means that you're making the proposals small, you're making them more local and local, then you would assume that under some reasonable continuity conditions, basically these z's become constant. So in some sense, it's close to being pi reversible. And this is then used to basically what you can do, because this is not simulatable in practice, you switch this ratio of pi's by a first order approximation. And this is what I mean when I say locally balanced first order Metropolis Hastings. So essentially, for a target that has a potential V, you basically you switch the ratio you switch the difference of potentials, right? That would happen here. You switch it with just a first order Taylor expansion of the same thing, and basically the normalizing constant changes, but basically what we're suggesting is using this as like a Metropolis Hastings proposal, right? So propose this and then put an accept reject step on top of it. And this, so basically it's a family of Metropolis Hastings proposals, which basically depends on the K, this density K, and it depends on the balancing function G. And it looks a bit out of space, but there actually includes some examples that you know. So basically, if you take G of t to be square root of t, and you take K to be standard Gaussian, this is exactly Mala. Maybe not be very clear, but that's exactly Mala. And the other option is something called Barker proposal that was proposed by Livingstone and Zanella in 19. It's like a really nice paper, in my opinion. Basically, they use this function GT, and they can use any K. And this is the only case of such functions when this normalizing constant is actually a constant. It doesn't depend on X. And it's possible to simulate and somehow to give you some flavor. It's like Mala. It's like a robust version of Mala. That's how to describe it. It's like Mala, but it only uses the derivative information to influence the direction in which they're sampling, but not the jump size of how far you're proposing. So to generate the proposal, they use the derivative to basically influence the direction, but not the size of the proposals. But we can simulate these things for actually any G of this form and for any Gaussian mixture K. At least for that. I mean, we don't actually, it's not like we have a full list of things that you can simulate and which you can't, but this you can simulate. This is simulatable. So this is going to be in some sense similar to Mala. You basically, yeah, it's going to be a bit similar to Mala, but you're going to have to throw some coins, whether you're like in this regime or this regime. It's not very, it's a bit tedious, but it's not very hard to see that this can be simulated exactly. So, and once you have one of these algorithms, right, you can do the same story as we did before. So you can basically, you can give it somehow product structure. It makes sense to basically, instead of basing it on the full derivative, you base it on the partial derivatives, and then you flip, and then you simulate each coordinate based on its partial derivative or not. This you can do, and basically, you get again in this situation where, in this toy setting where you have a proposal and a target which depend on, which have a product IID structure. And for any such algorithm in this class, you can basically show that it has an optimal variance scaling rate of n to -1/3, like Mala. I mean, now it's different. Now I'm assuming like it's smooth enough. I don't want to talk about what that means, but it's smooth enough. It scales as n to -1/3. And it scales, and it gives the optimal acceptance rate of 0.574, so the same as Mala. And then it makes sense to talk about asymptotic efficiency, right? So we have a family of these methods, and they will give you the same rate and the same optimal acceptance rate, but the actual, there will be like some term that you can call asymptotic efficiency. So in the limit, one will work, I don't know, 60% better than the other, or stuff like that. So it's like it's valid to ask yourself which of these things is the best, like which of these algorithms is actually the best. And actually, this asymptotic efficiency depends on the target, right? It actually depends only on these three quantities, A, B, and C. So these integrals, integral of first derivative, second derivative squared, third derivative squared, and then like a product of these three derivatives, and always integrated with respect to pi. It depends only on these constants, and it depends on the construction of the proposal, and it only depends on the fourth and the sixth moment of the density k, and it only depends on the value of the second derivative of g at 1. So it depends on nothing else than these things. And you can basically then, like I said, you can ask yourself, given a target, right, which means in this sense, given these a, b, and c constants, what is the best choice for k and g? And for example, you can ask different choices. You could fix the k. For example, you can fix the standard Gaussian. So in this case, you have k4 is the fourth moment is 3, the sixth moment is 15. And then it turns out that the best balancing function will have this g. So the second derivative of g at 1 will take this value, which basically you can then simulate by using by using this function and this a in the function, which it's not clear if this is always positive. To be honest, we don't know, but it is at least in certain cases. For example, if the target itself is Gaussian, then c equals 0, and you have minus 1/5, and then you have something here. So the point is that if you want to sample from a Gaussian, then actually Mala is not the optimal. This is something else here that is better. Mala is too conservative in some ways. It should go even more in the direction of the gradient somehow. And on the other hand, you could fix the balancing function. So basically, if you look at the Barker proposal from Giacomo and Sam, then the second derivative of g at 1 equals minus 1/2, and the best density to use, the best k to use, actually turns out to be Rademacher. So basically, you end up the optimal being this weird thing that is basically not it's not irreducible anymore, because it stops being a density. It happens to be -1 or 1 with probability 1/2. Now, of course, this is irreducible, so you're not going to directly use this, but you can use like a mixture of two Gaussians, right? You can use a mixture of two very thin Gaussians, and we've actually tested this, and it actually outperforms the other ones. It's really weird. And if you think that this is weird, then if you look at the global optimum, it's even more weird, actually, because the global optimum is actually given by you choose the fourth moment. You just choose some constant bigger than 1, and then you use for the k, you use what we call 3-point density. So you use something that takes only value 0, square root of k4 minus square root of kappa 4. And so some probability of staying where you are and some probabilities of moving symmetrically to some distance. So these densities actually are the ones for which the fourth moment squared equals the sixth moment. So this is why this comes out of the basically optimal analysis. And after you have this, you have to choose the G2 prime of 1. You have to choose it according to this. And basically, once you do all this, you can basically limit k4 to 1 in some sense. You can do this for every k4 bigger than 1. You cannot do it specifically for 1, but you can do it for any k4 bigger than 1. And if you approach 1 along this weird curve, you get a better result than if you're using Rademacher, because you could say that, okay, sure, if you're limiting k4 to 1, basically, that you're going to get something that you would think that you'll get Bernoulli out, but you don't. Not the Bernoulli, this Rademacher, but actually it looks like you're converging to it, but you're not, because you're using a different balancing function than you would be in that case, and you get to a better result. I mean, I don't think this is realistically implementable, but it's actually funny to see that in the toy cases where you can actually implement this actually does outperform the other thing. So this is still work in progress. We're not claiming that we're really understanding this well, but we have tested these things, and it works. And by the way, there's a mistake. So this should be on the bottom line, and this should be on the top line. So the probability of 0 should be this, and the probability of these two things should be. So it's like this. This equals that, and those two things equal this. And okay, so just to summarize, so we've demonstrated with Willfit that MCMC methods may perform worse than expected if the targets are not sufficiently smooth. And there still seems to be a scaling phenomenon, despite being a different scaling phenomenon than classically. Is this typical? We think it is, but yeah, who knows? And so secondly, in that paper, we have a framework that's capable of addressing optimal scaling questions for quite general Metropolis Hastings settings in a very detailed way. And it can even depend on a random environment. So, I mean, I've shown you two examples. One is to deliver those counterexamples, and one is to basically for these locally balanced things. And finally, the counterexample paper includes a generic way to construct counterexamples. And this kind of way of generating counterexamples could be applied elsewhere to answer MCMC questions, to provide counterexamples. And what is going on at the moment? So with Willfit, we're trying to build a unified approach to optimal scaling of Metropolis Hastings methods. We're trying to do this using the Dirichlet forms. So what we would like to do, for example, is we had some results here for these counterexamples. We would like to be able to show that there's a diffusion limit as well, but we can sort of do it for the classical cases, but for these anomalous cases, it's still eluding us, although it feels like we're almost there, but it's quite hard. So then with this framework, you can target the optimal design of Metropolis Hastings samplers, like these ones, locally balancing first order Metropolis Hastings methods. And I would be very interested in extending this work to other MCMC methods. So for example, can you create different random variables than these raw random variables that basically don't preserve reversibility, but a different form of symmetry? I think this is possible in some cases, but I haven't had time to do any of it because I feel like I still don't understand fully even the Metropolis Hastings case, but I think this is doable. And then finally, it feels like there is a link between MCMC performance and local sampler information. What I mean with this is somehow Mala, for example, uses more local information than Metropolis Hastings because it uses the derivatives as well to influence where it's going to propose. And Hamiltonian or stuff uses even more potentially. And on the other hand, you have various cases where the scaling is worse. One is noise observations. So this is you can see this in pseudo-marginal Metropolis Hastings, for example, right? You get less information from your location about your next target because you observe your target noisily. Second is in case of roughness, as we showed here with Willfit, and the third example is in case of discontinuity. So there's a paper from Roberts and Peter Neal about that they are constrained to a hypercube, and when you're close to the edge of the hypercube, which in the limit you're all the time, there's a discontinuity next to you. So you kind of, if you cross that discontinuity, you just kind of lose all the information. So I think that there is it makes sense to conjecture this sort of link. The more local information there is available, and the more you're using, the better the sampler is, the better the MCMC performance would be. Okay, I will end here. This is the list of references. I shall torture you no longer. Thank you.